Thanks a lot, and what, Salamat Swari? Salamat Swari? Oh, we give an introduction? Oh, okay, I'm sorry.
Check, check. Okay, good afternoon, ladies and gentlemen. Okay, today this is the last session for this conference, and this session we have another great keynote speaker who is Dr. Jason Scott. Before we listen about his presentations, I would like to read the brief descriptions about Dr. Jason Scott. Dr. Jason Scott is from USA, Alaska, and he graduated from University of Montana for master degree, and he got PhD program from Utrecht University, Netherlands, and he ever joined in NASA for postdoctoral programs, and now he becomes a Observatory of Singapore in Nanyang Technology University, NTU, and his expert is igneous petrology and geology. And okay, without further ado, I want to welcome Dr. Jason Scott for deliver his presentations. Again, the time is yours.
Okay, okay, so in giving this talk, an English word came to mind that's not such a common word. That's charlatan, which is a fraud, because I'll be talking about geochronology surrounding the last magnetic reversal of the Earth's geodynamo. And I'm neither a paleomagnetist nor a geochronologist. And so I don't know if I'm licensed to talk about this, but let's give it a try. We're going to be jumping topics a lot. And so, I'm just warning you ahead of time that what's coming along. First, the introduction, we'll talk about the reversal itself, we'll talk about geochronology, and then we'll move into talking about volcanoes that erupted around the time of the magnetic reversal. And those are in Sumatra and Laos, so we'll be moving geographically as well. And then we're going to start talking about asteroid impacts that happened around the time of the reversal too. And then, the talk will just evolve into crazy speculation at the end. So that's the ride. So the Earth's magnetic field emanates from the outer core, which is liquid. The most stable configuration seems to be this axial dipole field. And so that gives us the impression that somehow this rotation, the movement of the liquid outer core, is coupled to the Earth's rotation, either the mantle or the core, and is spinning along the same axis. And so that's the most stable configuration of the magnetic field due to the Earth's spin. It's the BM reversal, the Brunhes-Matuyama reversal, is a separation between the Brunhes and the Matuyama crons. It's the most recent reversal of the Earth's magnetic field, about 0.78 billion years ago. And like all reversals, the processes, why it happened, it's poorly understood. But it turns out that a reversal, it's not an instantaneous event. Actually, the final full reversal, which took place at 772,000 years ago, is actually the culmination of 22,000 years of irregularities in the magnetic field. It's the most recent reversal, so it's actually the only reversal where our current geochronology can separate discrete events within the reversal, right? And so it's the best one to study because, again, if you're using a technique with 1% precision, that's already plus or minus 8,000 years. So a 16,000 year time span is most of these events. So if we want to discriminate between these events, we've only got this last reversal to work with. So that's why it's important, or that's one of the reasons why it's important. Again, the chronology of the reversal is like this. We have 3 quick reversals, an instability in the field around 794. It seems to stabilize. And then at about 784, it collapses. The intensity decreases. And then finally, the field reverses at about 772. Now, these are measurements of field intensity from various lavas and sediments. This is beryllium 10, which is I guess an inverse proxy for field intensity. So the more beryllium 10 you have, the less magnetic field you have, and the reason for that is because beryllium 10 is produced by cosmic rays, by spallation from oxygen and nitrogen in the atmosphere, which then falls to the earth. It's trapped in ice cores, it's trapped in sediments. Ordinarily, if we have a strong magnetic field, we're shielded from both the solar wind and cosmic rays to some extent, but when this field starts to collapse, there's a lot of radiation coming from space, so you get these cosmogenic nuclides building up. So, beryllium 10 is a proxy for the magnetic field, the intensity of the magnetic field. So again, what happens during a reversal? The truth is, at least from my perspective, we don't really know what happens during a reversal. Here are some simulations. Oh, I'm sorry. This is going back. Some simulations, that would say, okay, we have a stable axial dipole. The intensity might collapse. You might develop a multipole. This might then gather itself back together into another axial dipole that might be normal or inverse polarity, the more stable configuration. But the thing about this is these are not just simulations, these are simulations that are driven by observations. So geologists are going out in the field, geochronologists are taking measurements, paleomagnetists are getting virtual magnetic poles. We're putting all this together into simulations, we're learning things, and then we're going back and focusing our observations. So although we don't really understand reversals, if we're going to figure them out, we got to work together on this. Paleomagnetists, people doing simulations, geologists, geochronologists. If we have any hope, it's that we all work together. So it's not just of interest to physicists, actually. So the reversal marks a fundamental change in the Earth's climate cycles. Not exactly the reversal, but the reversal period is where we transition from 41,000-year climate cycles to 100,000-year climate cycles around this time. So a lot of paleoclimatologists are interested in this period of time too. And the truth is, we don't really understand why this happened. There's not really a clear driving mechanism at this point. But these 100,000 year climate cycles allowed for ice to form near the poles, and so that allowed us to have ice ages, which then drove the evolution of life on the planet, perhaps ourselves included. And of course, the transition from these 41,000 year climate cycles to the 100,000 year climate cycles have to do with the preeminence of this orbital eccentricity cycle over the preeminence of tilt. So before, tilt was the most important thing that was governing the climate. The Earth's tilt, suddenly the eccentricity of the Earth's orbit, how elliptical it is around the sun, became the most important factor around this time period, and that allowed for the ice ages. So for dating around this period of time, we've got some options. So it's too old for a lot of techniques. It's a little bit too young for uranium-lead still. That's got a lot of air. Cosmic ray exposure ages work in some cases, but they also sometimes suffer from poor accuracy. So techniques like this, especially techniques with a gas decay product, those are good for dating volcanic rocks, and we've elected to, and of course they're good for dating volcanic rocks because volcanic rocks come up hot, so they're already degassed. So if the daughter product of the radiometric decay scheme that you're measuring is a gas, then as soon as the lava cools, the clock starts. So you're dating exactly the eruption, whereas something like if you're doing uranium lead on zircon, these zircons can hang around the volcanic system for hundreds of thousands of years, so you don't really know what you're dating. In this case, we know what we're dating. We elect to use argon-argon. We work with Brad Singer and Brian Hika in Wisconsin. This is their lab. Yeah, so the argon-argon method is effectively the potassium-argon decay scheme. So it's similar to the old potassium-argon dating that people used to do. The half-life is 1.3 million years. In order to do these measurements, you have to irradiate the samples, so we can't do it in Singapore. So we send it over there. These are their measurements. They have a multi-collector mass spectrometer. They're measuring 5 isotopes of argon at once. Really all they want to measure is the argon-39 derived from potassium-39 in the reactor. So that gives them the concentration of potassium. And then they need the concentration of argon-40, which was derived from potassium-40 in the rocks. So these are the two things you want to measure. Everything else you're measuring is actually a correction. So the correction procedure for this technique is a little bit complex. Okay, this is the second part of the talk. That was the introduction. Now we're going to talk about some volcanoes that erupted at the time of the reversal. And volcanoes are important for this work for two reasons. First, big explosive volcanic eruptions can produce these regional tephra layers that become marker horizons, drill cores and ice cores here, so we can correlate the paleontologic record here in this ocean drill core with the climate record from ice cores using this tephra horizon, a little volcanic ash and ice core. If we know the precise age of these things, we can then correlate records, these different records from different parts of the Earth. So precise geochronology is important when we start talking about stratigraphic markers of tephra. And right around the time of the reversal, we had two very large volcanic eruptions, the Older Toba here in Indonesia, and then the Bishop Cup back in America. These were really big eruptions that produced regional tephras. There are many more small eruptions, so there's plenty of volcanism to work with around this time period. But more than just tephras, we also look for lava flows and welded tuffs. And these are interesting because they contain thermal remnant magnetization that can give us a virtual magnetic pole. So it's like a fossilized magnetic field. And more than being a fossilized magnetic field, it's a fossilized magnetic field that we can date. So it's like taking a picture of the magnetic field at that time. And so we look around the world for these lava flows that happen to cool at the exact time of the reversal. And if we get enough of them, we can get a chronology of the reversal. And that's what people are trying to do. And I'll note that Indonesia, and Sumatra in particular, is one of the best places to look for both these tephras and these welded flows, because the tephras, because it has a lot of large explosive eruptions, and also because the periodicity of these eruptions is long enough that the deposits don't get entirely covered by more volcanoes within the last 800,000 years. So we start with a big one. This is Lake Toba. Hamdi brought us there in February. It was a fantastic trip. It was so great, in fact, that one of our PhD students, Marcus, he's going to do about 2/3 of his PhD on Toba. He planned on working on drill cores, but then we'd gone there. We discovered that there's still a lot more to do, and so we're going to continue working there. This is the older Toba tuff, right? So this is around 800,000 years, around the time of the reversal. The distribution of ash was something like this, so it's an important stratigraphic marker for drill cores. Here, when we're looking for it onshore, this is an old map from Knight et al. In the 1980s. They went and mapped the polarity of these deposits surrounding Lake Toba. I've highlighted all the reverse polarity in blue, so this is prior to the transition. It could be the older Toba tuff or what's beneath it. And then we've added the strat columns of Chesner, which come from later work. I've colored the older Toba tuff in pink here. And look at these thicknesses, hundreds of meters thick, this deposit, the older Toba tuff in some cases. I've modified the strat columns a little bit here to take into account another occurrence of older Toba tuff to the north that's actually now thought to be a separate unit. This is a paper by Mark et al. They recognized that the Toba ashes are actually a doublet in drill cores. It was 2 eruptions. And that's consistent with the geology developed by Chesner, where you had eruption of sort of the Porcia caldera, it's the proto-Toba caldera. It's a big eruption of OTTA at about 792, followed about 6,000 years later by a smaller eruption to the north at Herrin of OTTB. And this is the chronology as it stands today, although we're working to be sure that this is actually correct. Moving a little bit further south from Toba, I guess 100 kilometers or more, this is some work done by Kyle Bradley, who's actually a paleomagnetist. A few years ago, he was working at Sippy Rock. He stumbled across this unconsolidated tuff here that he thought might be older Toba tuff, distal older Toba tuff. So around Lake Toba, the older Toba tuff is welded, it's hard. Here it's soft. Of course, yeah, you can assume it's the older Toba tuff. We dated these sandodines in here, and actually it's a bit older than the older Toba tuff. So there are a number of large eruptions in Sumatra around this time. And there's some confusion that we need to sort out. I guess in order to use these things as effective stratigraphic markers, we got to know which is which. So moving away from Indonesia, when you think of Southeast Asian volcanism, you're thinking of Indonesia mainly, and you're thinking of the Philippines. You don't think so much about Thailand, Cambodia, Laos, and Vietnam, but there's actually a volcanic province there as well. So Thailand, I don't want to dwell on this too much, but you get a scattering of dates. You get a lot of small volume, isolated volcanic centers. It's hard to work out a systematic to all these little volcanoes that are erupting in Thailand. Vietnam, Laos, and Cambodia is much more voluminous volcanism. And we start looking at the dates coming out of some of these. And a lot of these volcanic centers, I'm going to highlight the Bolivian in particular, this one's been active for 16 million years, which is a really long time for a volcanic field to be active. And it's erupting different products too over this time period. So if we compare it worldwide with other volcanoes and volcanic activity, we can see, hotspots will be active for millions of years, but they'll jump from place to place. It's not so often that you have one volcanic field that just keeps squirting out lava for such a long period of time. The best analogy might be the Massif Central in Europe, where you have there you have a clear Graben situation. That's not the case here. But anyway, that's what's unique about the field. And so here we're in the Bolivian. We're looking at these stacks of lava flows that have been sized by the stream. Of course, it's volcanic soil. It's relatively high altitude, so it's a great place to grow coffee. And this is one of the premier coffee growing regions of Southeast Asia. Here's a map of the basaltic field. I apologize that the legend in this have cut it off, but it's a really big field. It's about 80 kilometers across, 9,000 square kilometers in size. It's lava pouring off a pre-existing sandstone plateau. We've got the lava flows broken into different ages by color. And what I want to point out here, one thing I'll point out is that we're also proposing that this is possibly the impact site of the Australasian Tectite. So that's a paper, hopefully, it's in revision right now. Hopefully it'll be coming out soon. Look for it, where I explain that story because it's kind of a long story. But what I want to focus on here are these three lavas, which we dated, which are within error of both this impact and the reversal. So these potentially recording the reversal. It's kind of remarkable that you have three lavas of the same age coming down different sides of the plateau. We're wondering if that impact may have triggered the volcanism. It's one hypothesis, but it might be difficult to do paleomag on these because we're working in the tropics. So anything that's 800,000 years old, it's been, largely sacralitized. You've got a few isolated core stones here and there. And I don't know, this is a question for you guys. Would you be able to do paleomag? Would you be able to get a virtual pull from these core stones? Inside, they're relatively fresh, but I don't know if they move around during weathering or not. If you looked at this core stone and looked at that core stone, would the field have the same orientation? I don't know. We haven't tried, but it would have different directions. Why do you say that? You think they've moved around during weathering? Yeah, that's the worry. And even at 200,000 years, you're already starting to get a lot of core stone development. This is for CT here. So here's what the volcanic field, or what a flow looks like after a couple 100,000 years. You can see the soil's nice and red. It's great for growing coffee. Here's an older basalt flow. This thing's been leached until it's yellow, and it's poor for growing coffee, actually. And only a few core stones are left in that case. Leaving volcanoes behind, we go on to impacts that are happening around the time of the magnetic reversal. And we can date these impacts by looking at tektites. So tektites are a glass that's produced by the impact. So an asteroid hits the Earth. It hits with such energy that it turns the rock into glass, and it throws this glass out into the air and makes a stratigraphic horizon. And the good thing about this is that it's a datable stratigraphic horizon because the rocks got so hot that all their gas is gone. So you've reset that potassium-argon system. All of the argon in these rocks is then decayed for potassium. So they're great for dating. And we look at the Australasian tektite stream field. This is the largest stream field on Earth. It covers about 10% of the Earth's surface. It seems to come from somewhere around Southeast Asia about the time of the reversal. Again, it says crater unknown. We think we found it, but it's not published yet. The stream field, you can look at differences in the tektites across the stream field. So proximal to Southeast Asia, you get these big Mong-Nong type tektites. They're blocky, they're high in volatiles. I held one in Bangkok that was 24 kg in size. So some of these things are enormous. Further out in the stream field, you get these aerodynamically shaped tektites, which are probably more what you're familiar with. Microtektites are recovered from drill cores. That's just a size thing. And then in Australia, you get australites. So the interesting thing about australites is they were melted twice. So they were ejected, they were melted upon impact, ejected actually into space, and then melted again on re-entry. So they get these funny little button shapes where they were melted and then reshaped by the atmosphere. Okay, so and you have these things in Indonesia. So these are beletonites or batu satam, as they're called, magic rocks. Is that what that means? Yeah, right. So this is something on this island of Biliton. Yeah, this is something they sell to tourists from Jakarta, right? You can see the price tag. This one's what, $250,000. They make jewelry out of these.
Quite expensive.
All right, so these things are found in Indonesia. They're found all across the region, and because they're such a prominent stratigraphic marker, they're attributed to all kinds of things, because anytime you're studying a phenomenon, you find a tektite, you could blame the asteroid, right? But, I mean, there may be some truth to this. They've been linked to these kill sites in eastern Thailand, where you have some small extinction events. They've been linked to the disappearance of Homo erectus here in East Java. And then true to form, China always profits from everything. So while it's linked to the disappearance of Homo erectus in Java, in China, actually Homo erectus developed better tools as a result of the impact for whatever reason. It was a change in the landscape, a change in the people, and they developed better technology, or that's one hypothesis. Of course, this impact deposit, it forms these soils in eastern Thailand, the Yasathan soils, which are important agricultural resource. They're rock-free soils, so they're good for growing things like cassava, kind of a drier soil. The impact deposit itself is prospected for bauxite in Laos. And this is what it looks like. This is an amazing impact deposit because you can drive around this region, you can find new impact deposits anywhere somebody has dug a hole almost, it seems like. This is what they look like. You've got this pebbly laterite layer, which you can see up close right here, overlain by this lust, which some Thai geologists have called catastrophe, because they think it formed as a result of the impact. The impact incinerated all the vegetation. It was a desert. You had all this dust blowing around at this time, and you deposited this massive bedding. You don't see any bedding in this lust. And then right at this contact is where you find where you typically find the tektites. And so this is the tektite here, right at the contact. Now in some cases they're a little bit below the contact, and often you see evidence of some energetic environment. You see these cobbles thrown in with these tektites. Again, I don't know if it's clear, you can see the contact of the list right here, and there are tektites here, there, and everywhere. And then sometimes the cobbles are a little bigger. Sometimes you see a layer of boulders associated with the tektites, so you get the sense that there is a lot of energy, actually. So this is an important regional stratigraphic marker. So we dated it here, and we also looked at some other mid-Pleistocene impacts that people have speculated were the same age as this impact. In some cases that's true, and in some cases that's not. For Zaman Shen crater, obviously it's much older. For Darwin, we think it's much younger. Belize turned out to be about the same age, and we'll come back to that. These are some things from the published literature here. So there were, a few different impacts around the world at this time. And we dated those. Our dates are here in red. So our tektite age is a little bit younger than most of the published literature. Maybe our beliefs is towards the older end. But what came out of this is that these impacts are within error of each other. Not only that, if you plot all of the individual dates that we have, you cannot discriminate these two events from one another. They're, for our purposes, they're simultaneous. And then, of course, here are the three reversal events. These are the excursions, the onset of field decay, the collapse of the field, and then finally the transition, which, okay, we can say that, yeah, that this occurred after this was all in progress. We also have this impact in Nicaragua that's a little bit older, seems to have happened before the reversal processes. Here's our Sippy Rock age, around 800,000. These are the volcanics going off. So we're developing a lot of chronology, a lot of stratigraphic markers for this time period so that we can better understand the reversal and so that we can better understand all the other things happening in this time period. And here we've got it correlated with oxygen isotopes. What's this? This is a temperature proxy. Is this beryllium-10? Yeah, so with field intensity. Oh. It moved over a bit. Anyway, this is the end of the legitimate presentation, and now we go into the part about crazy speculation. And so, you know, when things are happening at the same time, it's easy to say that they're related, right? And so the tendency here is to blame asteroids for everything. So we're gonna speculate about whether we can blame asteroids for everything that was happening at this time period. Of course, as your chronology gets better, you become more, I guess, justified in blaming that. So if you have two things that are happening at the same time, that doesn't necessarily mean that they're related. If you have two things that are happening at exactly the same time, it starts to suggest that maybe they are. So let's evaluate each of these questions and see if there's some truth to it. Okay, so question one. Could this impact in Laos have triggered the older Toba eruption some 1,500 kilometers away? It's a long way, right? Now, we know that seismic triggering of volcanic eruptions is a real thing. It's been documented. This is straight out of the usgs.gov website. We can say that an earthquake of magnitude 6 or larger could trigger a volcanic eruption at a nearby volcano if that volcano is ready to erupt anyway. Okay, so was that the case at Toba? Right now, there's some disagreement between the different ages. The Toba ages, we've got a different age for tektites and other people. We're still trying to figure out what's going on. What got people to start speculating that maybe, we're not the first people to say this, that maybe the impact triggered the older Toba eruption is that you find the microtektites right underneath the ash layer and even intermixed with the ash layer in ocean drill cores. They're right on top of each other. If we try to reconcile that with the geochronology, the only scenario that makes sense where you can get the tektites older than at least one of the Toba eruptions is if you use these dates for the tektites and you say that, okay, this is the OTTB eruption, and OTT happened early, OTTA, the large eruption, happened earlier, and it's not expressed in the core, or we don't know about it. And that fits with the geology, how it erupt. Okay, so the scenario would be OTTA erupted, forming this caldera, but there was still some magma hanging around. Later on, an impact came, shook this up, and there was a little eruption here that formed this little doublet that you see there. Okay, maybe. We need to figure out the geochronology here, so we still got work to do. We don't know if this is really true. But, impact triggering of volcanism has been proposed before, and the most famous example are these papers that are coming out about the Chicxulub impact and the Deccan traps. This is a few years ago. There were a couple of papers. This one was in Science, where they saw an acceleration of volcanism following the impact that killed the dinosaurs, right? And people argue whether it was the volcanoes or the impact that killed the dinosaurs. The impact was in the Gulf of Mexico here, and at the antipole at the time, things move around at the time, at the antipole at that time was approximately the Deccan Trap. So maybe that all this energy was refocused on the other side of the Earth, and it shook this volcanic system, which was already active, into becoming more active. That's the hypothesis. But that's a much larger impact than what we're talking about here. Okay, and so, yeah, what's the answer here? Was Toba triggered by the impact? Well, it's a good hypothesis, but we'd like a little more evidence. So yeah, the geologist will say, okay, let's go to TOBA, let's look for the tektites. The tektites should be on top of unit A, underneath unit B. The physicist is going to say, okay, well, I'm going to go do some more calculations. I'm going to see how much seismic energy is transmitted over 1,500 kilometers. So again, working together. Okay, question number 2. Was the reversal itself caused by the asteroid impact or a series of asteroid impacts? And again, this comes from ocean drill, of course, where we've got the tektites right below the reversal. And people have been talking, people have been arguing about this for decades, right? So we're not the first to speculate this at all. This is mainly driven by the Australasian tektites and the BM reversal, but people have also tried to link the Ivory Coast tektites and that impact with the earlier Jarmillo reversal. And I guess as a generalization, I would say geochronologists tend to like this hypothesis because you can use data with large error bars. And of course, you're going to overlap with some, I guess, geodynamo instability, and then you can publish it. Whereas modelers who already have a model for reversals, they don't want you to introduce an asteroid there. They say, oh, we've already got reversals figured out. We don't need an asteroid. So I think that's where the argument is now. Now, if we look at our tektite ages in the context of the GITS magnetic time scale of Singer et al., okay, this Ivory Coast date has so much error that it actually overlaps 4 subcrons, right? So it's hard to say whether there's a direct relationship. Our ergozite date is fairly precise, doesn't seem to be associated with any geodynamo instability. Now, if we look at the Australasian and the Belize, which again were at the same time period, we see that they occurred between this precursor, those 3 reversals, and the final reversal. So obviously they didn't start this whole process. They couldn't have kicked off this reversal because this reversal was already underway by the time these 2 events happened. Now we've got this other impact here slightly before that, which is actually before this. So we start to wonder, okay, well, we're starting to see a lot of impacts. We've got 3 impacts in a short period of time on land. But the Earth is 2/3 ocean. So maybe we've got another 6 impacts that we don't know about. So 9 impacts, we've got, is it possible? Is this a bombardment episode? Right. Okay. So at the moment, the geologists, I guess we both say we need more data, but actually, since we don't really know how a reversal works, even with more data, we probably wouldn't be able to say if the impacts triggered the reversal because we don't know what causes reversals. So it's unsubstantiated, and it probably will be no matter how much data we collect. That's my opinion, but feel free to disagree. Okay, then finally, our question number 3. Could this series of impacts, the same one we're talking about, could it have caused the mid-Pleistocene crisis or the mid-Pleistocene climate transition? Okay, so when we start taking in these 3 impacts, this is with air, we see it's starting, these impacts are starting about the time of this climate transition. Maybe 3 impacts, maybe 9 impacts total, like I say. Again, the driving force for what caused this transition is not understood at the moment, but it has to do with the either increased eccentricity or decreased tilt of the Earth. Again, this is the eccentricity, this is the tilt. We started favoring eccentricity over tilt. I did my own calculation. So how this would work, I guess, if the Earth is orbiting the Sun, you can imagine a tail of impactors. Now, we see this all the time, right? That's what the meteor showers are. So this is an old comet tail that you're going through. But those are pea-size impactors. You might have the same thing of larger impactors, and maybe you don't hit them every year, but maybe every 1,000 or 5,000 years you're smacking into a big one at the same point in your orbit. So over time, could that deflect your orbit a little bit? Could it make the Earth's orbit more eccentric? Well, I attempted, again, I'm not a physicist, I attempted some of my own calculations of this. So for just using inertia, a 10-kilometer asteroid traveling at 30 kilometers per second would only change the Earth's eccentricity by some small fraction of a percent. The eccentricity presently is about 2%, so this is not much of an effect. And it would only move you, something much less than 1%. It would increase or decrease the solar irradiance by well less than 1%. So I don't think this is enough to have much of an effect. And even if you had 9 or 10 of these impacts, you would just move 1 decibel over. It's still not really a big effect. So I'm going to go with no on this one. I don't think so. I mean, just maybe. Feel free to do the calculations because this is done in Excel on my desk. Probably I screwed up the units. It's a valid. I mean, it's something to investigate. But okay, at the moment, I'm going to say probably not. And of course, yeah. Then there's always some wise guy that says, "Okay, well, I told you so. You guys can't just go around blaming asteroids for everything." And of course, the correct response to naysayers is always, naysayers are, they're not, it's not productive. And so I think that anytime we can look at terrestrial phenomenon and search for a link or investigate a possible link with extraterrestrial phenomenon, I think it's worth doing because the Earth itself is not a closed system. The Earth is interacting with the heavens now and always, every day. And so we can look for extraterrestrial driving mechanisms to terrestrial phenomena. And I think it's worth doing it, and I think investigating the reversal may help us with this.
Okay, please big applause to Dr. Jason Scott. Okay. Thank you very much for Dr. Jason Scott. That was very interesting and interactive talk. Okay, now I open the sessions of question and answer. Is there any questions? Okay.
Thank you. Maybe I will ask you a little bit far from your presentation. If I saw from the Associate Professor Nurjana and then Professor Baba Musta and the other speakers, in their presentation, in their slide, always have picture hammer in the ground. Is there any philosophical meaning about that? Thank you.
Yeah, right. So when you go to field camp and learn to do field work, you learn that every photo has to have a scale reference, and it's useful. So actually, the best thing to have with you is a small ruler. But a lot of times when you're out in the field, if you had a ruler, you probably dropped it or something. But what you do have with you is your hammer. So if you know the approximate dimensions of your hammer, you put that in the photo. You take the photo, and then later on, if you want to know the size of the class and the laterite or something like that, you can measure your hammer, and then you can measure in the image you would know the size. So it's a scale reference.
Thank you so much.
For larger outcrops, you use people. Yeah, right. But you have to know how tall they are.
Okay, any more questions?
But don't ask about hammer. Okay, Jason, it is a very impressions, last talking it is.
I guess makes Rosie fokus atau fokus because okay.
Thank you, Jason. I have some questions like when you talk about impacts and makes greater velocity to eruption of the volcanic, right? How we characterize generally, a global characterize how we can differentiate between the volcanic because of outside factors like impact, and then the other is about inside factors. How we can distinguish?
Right, and yeah, the problem is, of course, we don't have a large data set because large impacts are so infrequent that we don't really have a good record of that. So volcanic eruptions and earthquakes we have a lot of, and that's where the USGS, they came up with that number. They say, okay, you need a magnitude 6 earthquake or larger near to a volcano that's ready to erupt anyway. And so the thing to do would be to say, okay, so what radius away from that could an asteroid impact occur that might trigger an eruption? But yeah, you're kind of, all of this stays pretty theoretical because we don't have so many examples. We have Chicxulub and the Deccan Traps, that's one example. We potentially have this as an example, and then we're arguing we also have in the Bolivan, perhaps if that's the impact site, we also have a small outpouring of basalt locally at the site. Which, you know, actually you see that on the moon. If you look up at the moon, you see it's parts of it are dark and parts of it are light. And so those dark things are where an asteroid is hit and created a crater that then filled in with basalt.
Because when we are looking to the characteristic of volcano in Indonesia, I mean they always have what is this? Caldera. So that's why. I mean.
Oh, you're saying that what we're looking at there, that's potentially. Yeah. I mean that's a totally valid argument. The counter argument for that is that we don't have explosive volcanism there.
Okay.
It's all very effusive, low volatile content. It just kind of bubbles out of there.
Yeah.
So we don't have any evidence of an explosive eruption, but we do have several lines of evidence suggesting that that location is constrained by a gravity anomaly. That gravity anomaly is at the center of a series of geologic observations, thickness of impact deposits. Actually more angularity in the tektites, a more energetic environment of the impact, and plus it's 800,000 years ago. It's a long time in Indonesia, but in Thailand that's actually not that long because the erosion rates are very slow. So if there were a crater there, you'd think you would see it. And it almost suggests that it has to be covered with something because it couldn't have eroded in 800,000 years. Our incision rates up there that we've gotten from this geochronology are about 0.05 millimeters per year. So in 800,000 years, you're only eroding 40 meters. And so if there were a large crater with a big rim, even a rim like the smaller crater that we see in Malaysia, it would still be there. As we see in Malaysia 1.8 million years later, it's still at the surface. So it almost has to be covered by something. So we've built a series of arguments to say that it's covered by a volcano.
Yes. Okay, thank you.
Yeah.
Okay, any more question? Okay.
Okay, thank you, Jason. Please go to the slide with erosion.
Oh, the eruption.
Yeah, erosion.
Erosion.
Yeah, slide. Black. Yeah.
Tell me when.
Now, back. Stop.
Oh.
After hammer. No, next.
Oh, yeah, right.
Next. Not this one. This one.
This one.
No,
Yeah, okay.
I don't like hammer.
So here we've got cone for scale. This is our driver.
Yeah, this one.
Yeah.
This is a very interesting data based on material science. We can see from the picture that there are several layer by layer, different color. In my opinion, I think this is because the different compound. So I would like to ask why be like this phenomena.
Okay, in this particular case, what we've seen at this, and it changes from location to location, every outcrop's a little bit different, is that, and actually maybe the best thing to do is actually to go back a little bit. Am I going back? I think it's stuck. Okay, now where are we? If we go all the way back, yeah, here.
Yeah.
Okay, so I think so below the tektite horizon, the color variation that you see, I think, and I think so what we've documented is that that's actually the in situ weathering profile. That's the lowermost color variation that we see, and I'll point this out here. So I think about up to maybe right about here is the in situ weathering profile. So these colors you see here. Now getting in here to this red, this is this pebbly laterite layer. Maybe, actually, probably just this uppermost red. I got to go look at the strat column for this particular outcrop because again, it's different in every case. This might be the pebbly laterite layer here, but in this case, on top of that, or in with that, you see all these boulders and things moving around. I can only imagine the processes responsible for that. You've got a lot of things. You've got shock waves, rarefaction waves. You completely denuded the landscape afterwards, so anytime it rained, things must have moved around. For a good decade after this, things were pretty, I guess barren and energetic, I suppose. So we don't actually know the nature of this deposit yet, and that's what amazes me the most, is that this is the world's largest impact deposit, and there's almost no literature on it. But you can drive around, you can find new outcrops every day, but it hasn't been well documented. The process that form these individual layers within this have not been described. So it's a wide open field to study. We've got a postdoc working on it now. There's a Japanese group, University of Tokyo, that's working on it now. But if this, I always compare it with Reese Crater in Germany. So Reese Crater, there's only a handful of outcrops. Each of them probably has 3 PhD theses done on it, right? Yeah. Here we can find new outcrops all the time. They're younger, they're fresher, there's a lot more we can say, but they're just understudied.
Okay, that was very, very interesting discussion. Any more questions? Enough? Okay. I would like to make a little note for these discussions that volcano can only be triggered into eruptions by nearby tectonic earthquake if they are already passed to Earth. Okay, finally we come to the end part of our presentation. We would like to thank again for presenter, Dr. Jason Scott, and all of audience here. And hopefully this presentation will be beneficial for all of us. Okay, thank you again for all of us here. Okay, the time and place I will give back to the Master of Ceremony. Assalamualaikum warahmatullahi wabarakatuh.